Hello, everybody. Hello, everybody. All right. Okay, so we're here now in a final stretches, and we have, I'm going to introduce the session because we want to make sure we're on time, because we want to end up with keeping everything quick and fast so that we can end up with Bill's slow archaeology. So our first presenter today is going to be Rebecca Bria from Vanderbilt University, and she's going to start us out, and we will hopefully keep everything rolling and on time. So thanks a lot.
Thank you. I hope everyone in the audience is not tired of hearing about digital archaeology in the Andes, because we have one more paper. First, I really want to thank all the organizers for inviting me to speak at this really exciting event. It's been a great experience. I've learned a lot, and I plan to implement, hopefully, a lot of the things that I've learned into future iterations of my project. In this paper, I review the benefits and challenges of using a digital data collection protocol to teach archaeological methods to university students. In particular, I reflect on 3 seasons during which I taught archaeology at my field school in Peru, using a mobile relational database and tablet system that I designed to document, manage, and analyze excavated data. First, I'll provide a brief introduction to my research project in field school. Second, I'll review the project's digital database and field collection procedures. And third, I'll provide evidence to suggest that students who use a digital and relational database to record archaeological data develop unique analytical skills that allow them to perceive multiple dimensions of the archaeological record. In 2009, I began PIARA, which is a Spanish language acronym that means the Investigative Archaeological Project of the region of Ancash, Peru. The PIARA project has focused primarily on the archaeological site of Hualcayan, which is located in a rural area of the highland Andes. Hualcayan has an exceptionally long history, nearly 4,000 years of continuous prehistoric occupation from 2400 BC until 1450 AD. The majority of our work at Hualcayan focuses on changes in ritual practice at the site in order to examine how ancient local people constituted and transformed the community between about 500 BC to 600 AD. That is, my project seeks to uncover the rituals that define community and constituted local authority after the decline of the religion and regional political network called Chavin, the proposed center of which was introduced to us earlier today by Matthew Sayre, and then during the emergence of the subsequent culture called Requai. In 2011, I expanded the project into an archaeological field school in collaboration with the National University of Ancash, or UNASAM, in Huaraz, Peru. Between 2011 and 2013, PIARA taught 8 field school sessions that were 4 to 6 weeks long at Hualcayan. Managed by a team of 6 to 10 staff members, each session had from 13 to 22 students who came mostly from the United States and in the United Kingdom, totaling 138 students over 3 years. Also, the field school taught archaeological methods to 45 Peruvian students, most of whom were from the UNASAM University in Huaraz and other universities in the capital city of Lima. The field school focused its student training in excavation methods and the analysis of ceramic artifacts and human skeletal remains. The field school concluded with a student-led research project. To collect and manage field data, I developed the PIARA database and digital data collection protocol in 2011 when tablet computers were becoming more affordable, durable, compact, and supported by a wider variety of powerful applications than ever before. In fact, I decided to develop a mobile database for tablets in the field after reading about the work of John Waldrot and Stephen Ellis at the Pompeii Archaeological Research Project, as many of us, I think, here were inspired. As I began researching how to execute such a database, I fortunately met Michael Ashley, who is also in this audience, and his team at the Center for Digital Archaeology. Michael was instrumental in guiding me and my collaborator, Catherine Dettori, pictured there, as we began to design a relational database for field and laboratory using FileMaker Go on iPad tablets. And I must say that Catherine Dettori, none of this would have happened without her. She was really, really amazing. We set about designing a database that would not only support my dissertation research objectives, but also benefit student learning. I developed this digital protocol and relational database for 4 reasons. The first is simple and obvious: to streamline and systematize the data entry process. But the second reason, the relational nature of the database, is more important. I wanted to be able to quickly search, sort, and relate the data during the season, thus allowing for a more holistic and comprehensive vision of the progress and process of excavations that cannot typically be obtained by using paper forms, at least not until the end of the season when all data are entered into a computer. Third, and similarly, I developed the digital database to directly associate the more objectively collected data, such as photographs, with the more interpretive and subjective data that is the work of archaeologists, that is, context descriptions, annotations, drawings, and notes. Fourth, and finally, I wanted to be able to link and instantly access all the different types of data that pertain to an excavation context, such as images, descriptions, and artifact data, in order to make more informed decisions during the excavation and help my crew chiefs and student collaborators see linkages between contexts situated within and beyond their current excavation unit. After designing and implementing our digital collection and management system, we discovered that it had a great impact on student learning. Before I review the specific ways it impacted the learning process, I'll briefly review the PRF FileMaker database and our digital recording protocol. As I mentioned, the PRF FileMaker database links a variety of data in multiple formats. However, because Wakayan lies in a rural Indian area with no available internet, as we've heard earlier today, and frequent power outages, there were some limitations to what we could develop and implement for this database. For example, we typically used 5 to 8 iPad devices at a given time, but because no 3G signal reached Wakayan, it was impossible to link all data across devices in real time. We explored the idea of broadcasting a local network as a substitute, but the mountainous terrain and the vast distance between the field house and the different excavation units made such a system impractical for our budget at the time. Therefore, we found it necessary to create separate database files for each excavation unit, which were loaded on separate iPads and managed by each unit's crew chief. This system worked very well for us, with the only additional limitation being that the various stages of laboratory analysis, including ceramic attribute analysis, had to be conducted on a separate database in the laboratory and then linked to the main database at a later date. Nonetheless, FileMaker's capabilities made it fairly simple to seamlessly link separate databases by cross-referencing unique identifiers present in correlating database files. We designed the database so that it linked a variety of analytical units. For each operation, the central unit of analysis was the cultural context, that is, any soil, architectural feature, such as a floor, fill, ashlands, or a wall section. All the data were linked to context in a one-to-many relationship as illustrated in this schematic. This is a simplified visualization of the actual relational links, seen here in the screenshot of the relationships graph in FileMaker. And this is only for just excavation, doesn't include other analysis tables. Next, here's an example of our digital context form. Context is one of many main tabs that you see up here in color. And each of the other main tabs pertain to a specific data type, including artifacts, special artifacts, carbon samples, and human remains. All of these materials or data types pertain, of course, to the context in which they were excavated. Thus, entered anywhere in the database, they automatically appear and can be edited in several of the subtabs, which you see down here in gray. So these subtabs relate to a particular context. For example, here in context 245, you can see how the main subtab that's already selected holds the basic information such as descriptions and interpretations, as well as its vertical and horizontal location. If I switch over to the special artifacts subtab, I can isolate the special artifacts that pertain only to that context. The built-in redundancy added a high level of flexibility to how the data could be entered, viewed, and sorted. As such, it also made it possible to view relationships between a variety of data types quickly and with just a few clicks on the screen. Other data tabs provide space for functions such as a context checklist, which I found absolutely necessary in order to ensure that crew chiefs complete all necessary tasks for a context, such as taking photographs or soil samples, all those things. We also use the tablets to create digital drawings and annotate photographs with context information. We produce these images using the iDraw application, which has precision drawing capabilities and the capacity to store different categories of visual information in 2 separate layers. In their overall execution, digital plan and profile drawings are the same as those produced on graph paper, yet a digital drawing has the added bonus of producing color images and publication-ready illustrations in the field. Using iDraw and other applications like Photogene as well to produce annotated photographs, this, however, provided us the greatest benefit over paper methods, in my opinion. For example, we annotated photographs to swiftly document the location of commingled artifacts and human remains. Because these applications provided for quick yet precise documentation of these remains as we collected them at every level and stage, we could then use these images in the laboratory to reconstruct depositional sequences by simply sequencing the images. While such documentation can be accomplished with measured drawings or georectified photographs, this system allowed us to gather very detailed information in complex layers without stopping to draw each new bone or artifact as they were uncovered. And I should mention also in these tombs where you can't really take photographs to georeference, you're kind of constrained, and so this worked really well for us. This approach has been instrumental in how we identify the artifact and bone patterns that correspond to ancient feasting or burial practices. Of course, paper drawings can serve the same purpose and be spatially exact, but the digital annotations allowed for ease and clarity of our data recording, particularly when measured drawings at each stage would have been impractical. In addition, by simply annotating images, we did not have to worry as much about differences in a student's drawing ability or patience while excavating complex layers of finds. This approach also provided a platform on which we could quickly compare, assess, and understand depositional sequences and stratified deposits, and ultimately make decisions about how to proceed during a very short field season. In addition, although all excavated contexts were recorded with the total station and photographed for georeferencing and GIS, they were also outlined and annotated in iDraw for visualization in the field. This proved to be a critical tool for documenting and interpreting contexts that were difficult to visualize in two-dimensional drawings. Such contexts such as the superimposed construction events in the central ceremonial mound at Wakayan is a great example of this. The mound contained closely juxtaposed features which were situated at the same elevation levels in many cases. But in these cases, they were built in disparate time periods. Take, for example, this rectangular space, which we'll call construction phase 1. These rooms were covered in fill and buried under a rectangular platform, phase 2. This platform was later refurbished, and at a later date, the platform was partially destroyed, and then the entire area was covered by a thick layer of fill and feasting remains, phases 4 and 5. All of these construction and destruction events lie at the same elevation, but they span almost a millennium. To document the juxtaposition of these features and keep them separate as we excavated vertically, iDraw images helped tremendously. For example, construction event number 2 that you saw earlier was a major platform fill event. It's made up of many distinct soil types, and soil and stone types, as indicated here. We wanted to carefully understand the process of construction and not mix the artifacts that pertain to distinct activities during the platform construction. Therefore, we could not excavate these soils as a single context. Although total station points preserve the precise location of these contexts in space, iDraw images on the iPad were much more useful as a guide for distinguishing and understanding the relationship between complex contexts as we excavated them. I should note that these grainy images were taken with the iPad 2 in 2011. The cameras on these tablets are much better now. And we did have the card readers for SD cards, but sometimes, when you're just in the flow and you want to get things done and move on, this serves our purpose, even though it's a grainy image, and I can always add in a higher quality image later and fix the lines if I wanted to. Finally, with these images imported, the relational database allowed for better data maintenance over time. The systematic, visual, and relational nature of the data collected with these digital tools allowed for new crew chiefs and students to become familiar with previously excavated data more easily. Because we excavated operations and architectural features that were quite deep and large, such as mounds, and because we continued to excavate some units for multiple years, it was essential to use a single interrelated system to store data and inform interpretations. So what does this all have to do with student learning in archaeology? First, I will clarify that I do believe field school instructors who use a digital format for data collection should also provide at least some basic training in traditional paper-based methods when it comes to, say, laying out a new unit or drawing a profile. After all, we cannot predict the kinds of projects students will assist on in the future, and therefore it is our responsibility to give them a strong foundation and methods that are transferable to any situation. But I also suggest that digital data collection methods deepen a student's understanding of archaeological contexts and material relationships, especially when paired with other data collection methods. There's a large body of research in teaching and neuroscience that show how people understand and retain concepts better when they practice and apply them using diverse techniques. Furthermore, a multifaceted approach to learning and doing cultivates more flexible thinkers who will be more open to adopting or creating new technologies in the future to solve similar problems because they understand that there are multiple ways that a task can be performed. Traditional methods aside, it is clear that digital recording technologies improve productivity and precision. I think we'd all agree. Yet beyond these virtues, I argue that digital technologies, in particular relational databases with high visual content, are not simply a means for more efficient data collection. Rather, they also increase critical thinking skills. This argument is similar to the debate over whether geographic information systems is a kind of software or whether it is a kind of science that has informed and influenced researchers a different kind of spatial awareness and analytical sensitivity. Now, to be clear, I do not mean to suggest that such technologies are changing human analytical potentials necessarily, but I would submit that they are certainly more than calculators, that is, just mere tools. And so we should consider through careful research the way that these technologies might bolster or hinder the learning process. So here are a few insights from my experience. During the PR Field School, archaeological research and critical thinking skills were most clearly revealed as students completed their final group research projects. For this final project, the students collected, analyzed, researched, and presented the analysis of excavated remains, all using project iPads with the database and PDF resources to do literature reviews. Students were also required to contextualize their findings within the cultural history of the region and then interpret the results within a theoretical framework to draw out the broader impacts of their original research. For example, students might choose to examine changes in the political dynamics of feasting by looking at trends in the shapes, designs, and distribution of ceramic vessels through time, either in a particular excavation area or between discrete structures. Or they might analyze all vertebra from a tomb to examine labor-related stress during a particular period associated with shifts in agriculture. For several field school sessions, students were encouraged but not required to use the database as an analysis tool. As such, we were able to use these final projects to gauge whether and how students could research, understand, and synthesize data using the PRI mobile database. We assessed the students by asking whether they were making first, second, and third order relations in the data. First, the students linking the different associated materials were the students linking the different associated materials of a particular context. Second, were they making connections between the materials or conditions of different contexts of the same operation? And third, were they recognizing similar patterning between operations? In addition, we also evaluated whether and how students forged linkages between the data they themselves had collected and the data collected during previous iterations of the field school. We consistently found that students who used the PR database excelled in all these dimensions of comprehension, and they were able to draw broad conclusions and link discrete contexts and data types across the site more than groups who relied on anecdotal data descriptions or who simply analyzed a discrete and narrow data set, but who did not contextualize those data by comparing them to the broader database. More precisely, the final projects revealed how students who used the database began to think in a relational manner about the data they were analyzing and presenting. Moreover, the database provided a powerful and immediate analysis tool for students. For example, the ceramic types of different architectural features could be drawn up and sorted to provide an estimated terminus post quem or terminus ante quem for a structure or layer that is the latest and earliest possible period to which a context or structure can date. Likewise, because we identified and cited human skeletal remains in the field as they were recovered, analyses such as minimum number of individuals could be immediately estimated by sorting and counting how many specimens existed for a particular bone element inside. While these functions can be completed in an Excel spreadsheet, the ability to then relate these data to other aspects of the database, such as architecture, artifacts, and stratigraphic level, made these functions in a digital database powerful tools for assessing and processing large sets of data that students do not usually have access to or that they could not otherwise process. The inherent flexibility of relational databases thus allows students to independently explore patterns in the data, which then leads to new insights and discoveries. Moreover, the tablets equipped with the FileMaker database and other applications provided students with an all-in-one powerful and collaborative tool to prepare, research, and then present their final projects. In sum, as I hope these examples reveal, a relational database develops more perceptive archaeologists who can immediately recognize and interpret different possible relationships between archaeological materials, contexts, and features. A relational database allows us to think differently and process more data at a time, to move quickly from particular attributes to broad patterns. That is, it allows us to see more relationships in the data at once, or at least with a few clicks of a finger on a digital screen. The digital technology then not only aids in in-field planning and interpretation, but also advances the analytical abilities of student archaeologists. Thank you. I don't know why I had lots of people to think on that slide, but it's not showing correctly, but thank you.
Rebecca, thank you.
Yes.
There's plenty of time for some questions.
Okay.
So there was a lively discussion on Twitter, and also a great, wonderful presentation.
Thank you.
And interesting to juxtapose maybe with the previous presentation for Sean. So anybody have any questions?
Sorry if I talked fast as well.
Hi, thanks so much. I'm wondering, so you talk about these student final projects and their interpretations of the raw data, and I'm just curious how you incorporate those interpretations into your larger interpretations of the site in the final publication.
That's a great question. In many cases, there are small insights that lead to a new direction. In some cases, you're really surprised at what a student has done, or these student groups. Sometimes they're analyzing data before specialists have analyzed them. So we're seeing these preliminary patterns. And of course, they're doing these analyses in collaboration with crew chiefs, myself. So there's a flow of ideas back and forth. But absolutely, I mean, they're creating new data as they do their projects, and then we build on that. So yeah, they're doing the archaeology, and it's a meaningful project. So not only do they learn, but the project grows from it. Absolutely.
Thanks.
Maybe one more question. Do you have time?
So have you, my jet lag brain is not coming up with the name of the author right now, but it's been suggested, and we're trying this on our research project, not on the IT project, but for training students in particular, embedding methodologies in the recording. I mean, what I mean by that is, like, if you want them to do what the soil texture's like, you don't just ask them, is it silty clay or whatever. You walk them through the USGS, soil analysis roll of sausage thing, and check and you take them through take them through it step by step, maybe with images to help. I'm thinking of like inclusions in ceramics. You take them through, is it rounded, sub-rounded, this sort of thing, and we've been reading about this and are starting to think that this is a really good approach. And I wonder, I saw it kind of with your checklist, and I was just wondering if you were sort of consciously doing that, or other examples that we may not have seen in the presentation.
Yeah, I mean, absolutely. There's that's the beauty of the FileMaker database. I mean, I had in there. It might take too long to go back to the slide, but. The flow chart to determine what soil that you're dealing with, and so you can just zoom in on your iPad and see the entire thing, and it can live in a small space in the database. Same with our ceramic analysis form. You can just throw a bunch of images of like what we mean by a closed vessel or an open vessel that live in that same form that you can just go to, expand the screen, see it, and then go back to your checklist and do the analysis. So yeah, that's definitely intentional, and that's not just for students, that's for crew chiefs, that's for myself, that's so that we can do good archaeology, yeah. All right.